letters, but what I want to show here is a sequence starting from the top left here with the letter G for horse cytochrome C and then human underneath. And what you have are the differences highlighted. I'm highlighting the differences here for you. So here you have the differences. So pretty much the protein is the same in a horse and in a human being, except for these small differences. And so they say, okay, we're not very far, evolutionary speaking, from a horse. Notice that there are just a few differences. The great majority of the amino acids, the letters are the same. So a G matches with a G, the D with the D, the V with the V, the E with the E. So yeah, there's a lot of similarity. So there we might say we have homology, and the evolutionists would say that proves evolution. The design theorists will say, well, that proves a designer has designed it, and they're reusing similar components. So let's look at homology in the bacterial flagella, where the debate it gets somewhat more heated. And we're going to look at similarities here, which suggest to evolutionists that we could evolve from, in this case, a flagella protein H from a part of, which is the flagella protein H is here marked with the arrow in the base of the flagella. It's part of the motor that drives the flagella. And they say this is very similar to the F-type ATPase F1 protein. And here we have a diagram showing the ATPase with the similar component. So they look at the amino acids and say, well, we've got similarities, or we've got enough similarities to claim homology. Well, how many similarities have they actually got? Here I have 3 sequences of amino acids. I hope you can see it. And I'm going to highlight the similarities here, not the differences. Before I highlighted the differences. Here I'm highlighting the similarities. There are a few similarities. Right? There's less than a dozen similarities there. So most of the sequence is different. Yet they claim there's enough similarity to claim homology, that the flagella protein H came from the F-type ATPase. Well, I'm sorry, the evidence is not nearly so strong as for something like cytochrome. I mean, you've got to take a big leap of faith to believe that. What they actually say is they look at different amino acids which are similar chemically, but actually different amino acids, and that's where the yellow marks are. And these are similar types of amino acids in the same position. Therefore, there's some sort of functional homology. But the argument is rather weak. And this assumes that you went from the type 3 secretory system to the bacterial flagella, and most of the evidence suggests that it's the other way around, that the bacterial flagella came first, and the type 3 secretory system is actually a degeneration which causes the bacteria to become pathogenic, which is quite an interesting concept if you're a creationist looking to explain how bacteria became pathogenic. But we won't go there, not tonight. But I want to return back to irreducible complexity because it's very important. It's a very strong argument. And I want to refer to the example that design theorists use. The mousetrap is an example of an irreducibly complex system. It's actually quite simple. So, and to refute Dawkins' claim that we can't demonstrate irreducibility, because it can be. It can be actually directly testable. I forgot to bring my mousetrap with me, so you're going to have to work with my slides, so I can't let you handle a mousetrap and play with it, but it's got various components. But we have to remember that not all complex systems are irreducible. And this is where Dawkins goes wrong. He thinks we claim they're all irreducible. And simple systems can be irreducible. This is why we have the mousetrap. Here's a mousetrap. It's got about half a dozen components. It's got a catch, it's got a spring, it's got a hammer, it's got a pivot, it's got a holding bar, it's got a holding bar attachment, and it's got a base plate. Take any one of those components away, and your mousetrap doesn't work. So that is irreducibly complex, or it's irreducible. I would prefer to say irreducible because when we use the term irreducibly complex, people sometimes get confused, and I think Dawkins has got a bit confused because he's confusing the two. Irreducibility is actually separate from complexity. And there are many irreducible mechanisms around us that we know are made by human designers. We manufacture them all the time. And the crux of the argument is when we know the source of an irreducible mechanism, it turns out to be a designer. Somebody made it. And there are lots of other things around that we don't know how they appeared. They appear to be irreducibly complex, they appear to be irreducible, but we have no idea where the designer is or how they arose. But we've never observed an irreducible system arise by natural selection, unless you assume natural selection in the first place. It's no good to say, well, look, we have all this stuff that evolved. Well, you're actually assuming what you're trying to prove. So if we find something that appears to be irreducible, it's very strong evidence there's a designer who made it. And that is the crux of the irreducible argument. And it's reasonable to assume that if we can demonstrate something's irreducible, that it was designed, and if it was designed, we need a designer. Now, some people are going to say, well, explain the designer. Well, that's a separate question. It's a good question, but it's separate. The demonstrating design is one thing, explaining the designer is something else. When an archaeologist digs up a stone tool, they don't have to see the designer to know that it was designed by somebody several thousand years ago. And that's the crux of the irreducibility argument that creation is used. But I want to move on now. Time is passing. The origin of life. The origin of life is a separate question from evolution, and Dawkins is quite correct to point that out. But it's still a question. Where did life come from? And interestingly, Dawkins' answer is luck. And that's what he says in his book. You can read it in the God Delusion. I don't have my copy with me. Do you have your copy, Paul? No, we haven't got a copy of the book with us, but he does have it. He says luck. He says once the initial stroke of luck has been granted, and the anthropic principle most decisively grants it to us, natural selection takes over. We'll come back to the anthropic principle in a minute. The origin of life, the cell with a nucleus and mitochondria, was an even more statistically improbable step than the origin of the cell with a nucleus and a mitochondria was even more statistically improbable than the origin of life itself. So he's saying actually we need a bit of luck there as well. Going from a bacterial cell to an animal cell, which is more complicated, we need a big stroke of luck too. And in fact there's quite a lot of luck required in Dawkins' story of life. But he claims that it's plausible. But actually I would say that his estimate of the probability of life is rather high. He puts it about 1 in a billion, which is quite generous. Highly generous, in fact. It's rather difficult to estimate the probability of life, but we're going to come back to that in a minute. He also says, well, given enough planets in the universe, we're going to have life evolving on some of them, even if it's very improbable. So if life evolves, the probability of life is 1 in a billion, and if we have a billion planets, you're going to have life evolving on a billion planets. Now that's basically what he means by the anthropic principle. He's saying that because there are so many planets, one planet somewhere is going to be suitable for life, and the planet that has life on it is a planet that's suitable for life. Because we're here to observe it, we must be on a planet that's suitable for life. That's basically what he's claiming from the anthropic principle. But he also, I believe, overestimates the power of natural selection, which is why I talked about natural selection earlier. Natural selection can do so much, but it cannot produce novelty. And it's not only creationists that are saying that. There's actually a group of evolutionists who are now known as the Altenberg 16, kind of heretical group, that's saying Darwinian natural selection doesn't work. We need something else. And I would agree, we do. I don't agree with their answer, but I agree we need something else. So Dawkins actually appeals to luck quite a lot. Lucky events in the history of life. Life appears by chance. The first cell with a nucleus appears by chance. But it doesn't stop there. To get from a single cell to an organism that's more than one cell, you need more chance. And he admits that. And segmentation appears by chance. Segmentation just means an animal made up different segments, like an earthworm. But that's quite a biological innovation, if you like. And it's, again, something that appears by chance. And he appeals to chance rather a lot. But he says, given enough planets, we can have chance getting us to where we are today. So even if it's very, very improbable, it's going to happen if we've got enough planets for life to occur on, because life must be evolvable. But he hasn't proved it. He's making that assumption. And one thing for me that says, well, hang on a minute, there's a bit of a problem here. Let's look at what we need to have the simplest cell, the simplest unit of life. What do we need? Well, there's actually a group who've been researching this, and they've published a paper on the minimal bacterium. Say, okay, we take a bacterium, and it's been published in the Proceedings of the National Academy of Sciences in January 2006 by a group owned by J. Craig Venter. He was one of the guys involved in the Human Genome Project, and he's trying to make life in the laboratory, which is an interesting exercise. But he says, okay, we want to make life in the laboratory, we need to know what we're dealing with. What's the simplest unit of life that we need to have for it to be sustainable? So what they did, they took a bacteria. In this case, it was a mycoplasma bacteria, which is a parasitic bacteria, and he started chopping out the genes by a process which we don't need to worry about, and he came up with the minimum number of genes required to sustain life. It's 382. Now that is probably an irreducibly complex system. Explain that, how that arises. If that's the minimum requirement for life. How do you get from chemicals to life if that's your